So can you, sorry. I think I have to turn off the lights. Sorry, I chose dark background. So I will keep it short because we are a little bit running out of time, but I hope this will be simple enough for you to just understand if I go through the slides so quickly. So here I'm going to talk about high-energy astrophysics, and I'm from the KTH Particle and Particle Physics group at Serena, and what my expert is in gamma ray bursts, but I want to tell you something about it. How do we really do high-energy astrophysics, astronomy? So how do we observe? Because we can't see X-rays, right? If you can see X-ray, tell me, or you're Superman. And so when we look up the sky, so this is what we see. We see the sun, we see the stars. They revolve around the Earth once per day. Of course, this is the Earth, which is rotating. But when you see the sky, you probably would sometimes think, so where does the light come from? Or do they only emit in visible light that we can observe? So these are the problems that the ancient Greeks, the great philosophers, also anticipated. And of course, they don't know about X-rays and gamma rays. But now we have, as the science advanced, so many scientists has figured out the physical laws of the nature. And for example, I think these scientists are famous enough that you all know about them. And the Newton found out the light can be separated into color light. So white light is composed of color light. And Einstein also found out that, okay, light can also be bent by gravitational waves. So we have already known a lot of the physical nature behind the observed, the observations. So people started to build larger and larger telescopes. So these are actually, I think this is one of the telescopes which Hubble used to discover the expansion of the universe. But we are not limited in visible light, of course, because we now know that light is electromagnetic wave. Of course, it's also particle if you know about a little bit quantum physics. So Newton thinks that light is particles. So the particle nature of light is actually proposed by Newton himself. But we know that, okay, if we look at, visible light or lower frequency light, they behave like a wave. But, what about the higher energy? In the higher energy spectrum of this EM spectrum, we have X-ray, ultraviolet X-rays and gamma rays. And so the X-rays are actually discovered quite recently only by this guy, Röntgen. So this is the discoverer of the X-ray. So in Chinese is 人孔, right? So 人性, 对. So he discovered X-ray, and actually he insisted to call X-ray X-ray. Actually, some scientists insist to use his name for X-ray. So in German, he's a German. So in German, X-ray is called Röntgen Strongen. So I hope my German is well enough. So this is his hand, and he's discovered X-ray has a great penetrability. So it can actually penetrate your skin. It is only stopped by the bones. So you can see the bone, see through the skin. And then this is his wing. Of course, it is also, so it shows that X-ray can also be stopped by metals. And there are a lot of applicability of X-rays. Like if you go through the airport security, you have to check your bag by X-ray. And also there are so many medical uses, but one of the application of X-ray is X-ray astronomy. So we can understand the universe through the eyes of X-ray telescopes. So what is this? This is the moon, right? And what is this?
It must be the moon.
Yes. This is the moon. This is the moon through X-rays. So it looks so different, right? So it is very interesting to look at everyday objects or the stellar objects in different frequencies that our eyes cannot see.
So they actually come from the sun.
Yes, yes, it reflects. Yes, exactly. So the moon itself do not emit light, no visible light, no X-ray, nothing. But what we see here is just the reflection of the X-rays. This is actually from the background of the solar system. So it reflects through the surface of the moon, and then we can observe it with X-ray telescopes, either ground-based or space telescope. So I'm actually going to talk about this. So again, this is the whole universe in visible light. And our galaxy is, our Milky Way galaxy is in the middle of it because we are inside it. So we cannot jump out of the galaxy and then observe the universe without it. But then when you observe the universe in X-ray or higher energies, for example, this one is the Rosette X-ray telescope. Is in a quarter electron volt. KeV is a kilo electron volt. So you see the universe behave so differently. So the Milky Way disappeared. So actually the most intense soft X-ray sources is not from the galaxy itself. It is from the other places in the universe. And then if we go high up in the energies, we see the galaxies again. See the galaxy again. And this is from egret, about 100 MeV, so million electron volt. And then this is Fermi, large area telescope with even higher energy. So you see, even if we are in the X-ray or gamma ray band, but if we change a little bit of the energy or the frequency we are using to observe, the same object can behave so differently. So we actually need, as astronomers, we actually need to understand the stellar objects in various frequencies. We cannot just say, okay, I'm an optical light astronomer, I don't care about gamma rays. No, you have to understand. You need to understand the nature of the objects in different bands in order to fully understand that what you're studying. So, a little bit unfortunate, and actually it is more fortunate than unfortunate that we cannot observe X-ray and gamma rays on Earth because the atmosphere blocks. So the high energy, most of the high energy electromagnetic waves from the universe, and it is fortunate that we cannot observe them on Earth, because if we do, then we will be already dead, because the high energy EM waves are highly lethal. So a little bit dose of gamma ray can kill you. So what we can do is just a few astronomies on ground. For example, the visible light, we can see the universe through the visible band, which is actually very narrow. And then some of the infrared, but not much. As you know, the atmosphere absorbs infrared. But we can do a lot of radio astronomy. So you see from the big movies that they're often big dishes of radio telescopes. But we cannot do X-rays. So we have to send the telescopes up to space. So here are a few examples of the earliest X-ray telescopes. So they're all put up by NASA, I think. I think one of those may be from the Russia. I don't remember, but this is the first one that I can find on Wikipedia. So it's called Uhuru. And it's up there in 1971. I think it lasts less than 1 year, and it just died because of technology. And then the second one, I think this is the second one. It's called Einstein, and it's also an X-ray telescope. And here another one. I just showed you the map of the universe, right? Remember the Rosette telescope is up there in 1990. And then if you notice, all these X-ray telescopes, they have one similarity. So this is another one. this is a Chandra, is still in operation. And then yet another one, the XMM Newton, in 1999, up there, still operating. And do you see one similarity? I show you again. Do you notice about one special feature from the shape? Yeah, they are all long. They are very long. They are all like the cylinder. And why? Anyone knows why? What?
Used for the solar energy.
Oh, you mean this one? Yeah, these are solar panels. Yeah, but what I'm asking is they are so long. But actually, this is a stupid question because the telescope is long, right? We use telescope, but it is actually longer than you expect.
Accent
Asset? What is that?
can make it fly more fast.
Oh no, no. There is no atmosphere of space, so whatever shape it is, it can fly like a bullet.
Is it because to lower the interference from low energy
No,
lights?
it's actually because of the nature of X-ray. So it is so difficult to focus X-ray. So just think when we look in the mirror, we are actually looking at the light reflected from the mirror surface, right? And do you remember that Röntgen himself put his hand under the X-ray, and then the X-ray just penetrate through his skin. So X-ray treat a mirror like nothing. It just goes through the mirror. But it actually does reflect a little bit, but just at a very high incident angle. So if this is a mirror, so just so this is the mirror. This is the mirror surface. So when you're looking at the mirror, you just stand here, and the light just like go through the mirror like normally, and then reflect normally, and then you see it from your eyes, right? But X-ray does not reflect this way. X-ray, if you emit X-ray like right through the mirror, it just go through it. It's transparent for it. For X-rays. But if you emit the X-ray at a very high angle relative to the normal of the mirror, then it reflects a little bit. So it is from this principle we can build the X-ray telescopes. So we put mirrors. We put loads of mirrors in concentric how to say. So we put many mirrors, and then each of them a little bit more narrower for its radius, and then so during each incident of X-ray it reflects a little bit, so the angle changes just a little bit, maybe 1 or 2 degrees, and then so we can focus it after a lot of reflection. So that's why we need really long telescopes. So the X-ray telescopes are often longer than 3 or 4 meters. So this is one of the I don't remember which telescope is it. This is a model of one of the X-ray telescopes I just showed you. You can see these laminated metals. They are the mirrors. So we don't use just one layer of mirror at each incident because we want to increase the sensibility and the intensity of the light. So we use these are actually hundreds of mirrors. So we focus the one source using hundreds of mirrors, and then we can only result in a very dim image if the source is not intense enough. But technology has advanced, so now the modern X-ray space telescopes, they are doing quite good, very good actually. So this is one of the very famous Crab Labella, and I think this is a composite image of visible and ultraviolet light. So here you can see a very dim haze on top of it. I think it is not visible light, but or whatever, I don't know. And these two images are in X-ray. So this is the Rosette telescope, which was sent up to space in 1990s. And this is the Chandra. This is sent from the late 1990s. So just 10 years separation, you see the technology advanced. So, but in both images, we can see one very, very intense difference from the visible image. It is here. We see one very intense dot in the center of the nebula, which in the visible light it is not there. It's just not there, right? We can see the nebula itself around it, but we cannot see the central source. It is actually a neutron star. So it only emits in high energy frequency. So that's why we need high energy telescopes. So what is neutron star? It is actually a sun, a very giant sun, much larger than ours, and then it dies. After it died, it shrink and become a neutron star, which is even smaller than Earth. But it contains a mass of it ranges from 2 or 1 point something to tens of solar masses. So you can imagine you're squeezing the sun into a volume that is smaller than the Earth. So this is, anyone know where is this? This map. This is a in scale comparison of neutron star. This is Manhattan, New York. It is smaller than New York, but it contains the sun. So this is the neutron star, and it emits in very, very high frequency. And this is actually why we need high energy astrophysics, because where do we find these astronomical X-rays and gamma rays? They often come from very extreme objects, because for ordinary stellar objects like the sun is very ordinary. It has so low energy, just nothing in the universe. But the stellar process happening on the sun is not energetic enough to emit in high energy like X-rays. Sometimes the sun does emit in gamma rays, but the different from the neutron star always emit in X-ray and gamma rays. And so a neutron star is very dense, as you can imagine, or you can't imagine. Actually, I can't imagine how dense it is because it's so dense. You're squeezing 1 solar mass or 2 solar mass in the volume of New York, and so every particles are squeezed together to a point, up to a point that the neutrons in the atoms touch each other. So the atoms are not atoms anymore. So you just imagine the electrons are being pushed into protons, so they merge. They combine to become neutrons. So everything is neutron. The neutron star is like a giant neutron. So and there are so many theoretical studies of neutron stars since a very early time. Like, for example, this is a standard textbook neutron star structure description, but some of the descriptions are already wrong in the modern sense. But the general picture is you have neutrons in the crust, and then you have a liquid core. It's like the mantle of the Earth, but it is not lava. It consists of superconducting and a superconducting superfluid of neutrons or some very heavy metals. And so you can imagine how extreme is these objects. And then if the neutron spins, it becomes a pulsar. And the pulsar is like a lighthouse in the universe. It spins so fast that it is even faster than the fan in your computer. But so imagine the sun is spinning faster than the fan on your computer, and then it's emitting X-ray and gamma rays. So it is very, very stable. Actually, the rotational period of the pulsar is more accurate than the atomic clock in your computer. So astronomers actually use pulsars to time. And so
I can tell them the Chinese of pulsars，就说那个高速旋转的中子星就会释放一个固定频率的射线，所以这些叫脉冲型。醒天的同学应该都听过，包括如果看过《三体》的话，就是咱们中国刚发了一颗卫星，就是测试脉冲星导航，这个是在以后星际旅行和那个行星探测非常有用的一种，因为它们位置固定，而且频率极其稳定，这些释放的一些射线极其稳定，所以可以用来星际导航。
Yes. So if we happen to be just at this jet, inside the line of sight of this jet. So if our line of sight is from here, looking at the neutron star, we see it as a pulsar. If we are here, we see it as a normal neutron star, or we don't see it. So yeah, well actually do you know the Voyager spacecraft? They are the farthest spacecraft, human-built objects. I think Voyager 1 is already outside of the solar system already. And so on them, there are metal planes fixed on the spacecraft to tell aliens where are we. So the map, so you can imagine how do we draw a map for aliens. And then on that map, I didn't show it here, but on that map, we mark several neutron stars positioned in the in the Milky Way on the plane, on the metal plane. So because, well, if the aliens are advanced enough to find our spacecraft, they must be advanced enough to locate accurately the neutron stars we marked on them, because each neutron star rotates in each different rotational speed. So if the aliens have a computer, they can just put in the positions of the neutron star and find out where the Earth is. And so talking about extreme compact objects, I would like to talk about something about supernova. So this is not our Milky Way. So this is another Milky Way. This is another galaxies in the universe, just one typical one. But then one day astronomers found out so before the supernova explodes, there's nothing here. But one day when some guy look up the sky looking at this image, he or she found that there is a very bright spot here, which dims out in the period of weeks or days. So it is actually one example of supernova. So a supernova is this is in visible light, and this talking about intensity. The intensity of this one single dot here is higher than all the stars, all the billions of stars in this galaxy. So you can imagine how energetic supernova is. And there are different types of supernovas. So the one of the more useful type is the type 1a supernova. And the type 1a supernova consists of binaries. So in the binaries, the two stars are of different age. So one of them dies sooner, right? Or you can have both of them die at the same time, but it's so rare. So in most cases, one star died and it becomes a white dwarf. If the star is not heavy enough, like our sun will become a white dwarf in 50 billion years. So, but panic not, because we are not going to see it. And so this is the future of our sun. It becomes a white dwarf, and the atmosphere of the sun will be blown off by the intense radiation of the central object of the white dwarf. And then if our sun has a companion, which is the sun, and if this giant star is close enough to the white dwarf, because of the huge gravitational attraction of the white dwarf, the material of the giant star will be attracted and form a accretion disk. And because if you know a little bit about our quantum physics, you know a white dwarf cannot be too heavy, just because of the reason I just told you when something forms a neutron star, because if it's too heavy, then the electron pressure cannot sustain its self gravity, and so the gravity of the neutron of the white dwarf itself will push everything into a black hole or a neutron star. So if too much material falls onto the white dwarf surface, it will become a black hole. And before it becomes a black hole or neutron star, it explodes. So this is where how the supernovas are formed. So this is another example of white dwarf. So this is Sirius A. This is the brightest star on the night sky that we can see by our bare eyes. Sirius, in Chinese is 天狼星. So actually, but it is not one single star. It's actually a triple star system. But I don't know where is the third star. This is Sirius A, and this is Sirius B. Sirius B is the white dwarf. So so they are close enough that they are mutually gravitationally attracted. And this is a very big blue giant star. It is much more massive than the sun. So in a million years or so, it will become a type 1a supernova, if the theory is correct. And why the type 1a supernova is useful is because astronomers often use the type 1a supernovas to determine the distance between stellar objects and us, because there is a limit. I just told you there's a limit of mass that a white dwarf can sustain, right? So you can expect every white dwarf explode at that same mass limit. So that means, if you think about the white dwarf as a candle, so it is a standardized candle. Every candle in the universe is of the same brightness, right? So if we see the white dwarf, the white type 1a supernova much more dimmer than what we calculate, it means it is much more further from us, right? So it's called a standard candle. And there are different types of supernovas. Here we have type 2 supernova, which does not require a companion star. Just one single star, like the blue supergiants, and it is too heavy, so it feels it can trigger a nuclear reaction with much heavier atoms than our sun can. Our sun can only fuse hydrogen or a little bit helium. But a blue supergiant can fuse atoms up to iron, and up to that point, it cannot fuse anymore. It cannot fuse atom into even much heavier atomic nuclei anymore, because it requires energy, right? Iron atom is the most stable atomic nuclei, as the human species knows. So up to this point, it can't fuse anymore. So it releases nothing. It cannot release energy anymore. So it cools down, right? So actually, up to this point, the gravity wins against the gas pressure, because it cannot feel anything. It cannot emit energy. So there's no gas pressure from the inside to outside, and then the gravity just pull the giant star, just squeeze it into a black hole, and then it explodes. The outer surface explodes, and the central part become a black hole. And then, but actually, a black hole is not black. A black hole, all formed by this way, often has an accretion disk around it. And the accretion disk, the matter in the accretion disk will be attracted into the black hole, but some of them will be emitted in relativistic speed. Means it is emitted so fast, very close to the speed of light, like 99.999% of speed of light. So, and this is just a consequence of conservation of angular momentum, right? If everything just spin in towards the black hole, inside the black hole, then the angular momentum disappeared, right? So something has to balance the angular momentum. So something has to be emitted in the jet, like just Serena just talked about the jet, remember? So so you can imagine this is even more energetic than X-rays. So we have another name for even higher energy EM waves. It's called gamma rays, and this is Einstein, right? Because well, one of the first discovered gamma ray is from the spontaneous decay of atoms, and it's actually just a consequence of E equals mc squared. So this is the 101 building in Taipei. See, E equals mc squared. This in, I think it's taken in 2005. It was the 100-year anniversary of special relativity. E equals mc squared. So in atomic nuclide, they emit gamma rays. And also in space, we observe a lot of gamma rays. So we send out probes to the space to observe gamma rays. So these are gamma ray space telescopes. Who can tell me the difference of them from the X-ray telescopes? They look very different. Huh? They do not even look like a telescope, but they are telescopes. Anyone knows why? This is cosine B. I don't know if it's cosine B, cos B. And then this is Vela. Vela is the first gamma ray, one of the first set of gamma ray telescopes to be sent into space by the US government. They were used to monitor any atomic test on Earth. But it just by incident, it observed so many gamma ray flashes from the universe, not from the Earth. So actually, what I'm going to talk about, the gamma ray burst, was discovered by these Vela satellites, which were military in use. And so I will tell you the answer why they do not look like a telescope at all. It is because, well, I just told you, X-rays cannot be stopped by a mirror, right? And gamma ray has even higher energy. So even if we use, well, if we want to build a very long gamma ray telescope, it is possible, but it has to be too long that we just cannot send it to space. It is longer than the rocket itself. How can we send it to the space? And it is not practical, right? And so we use another method to detect gamma rays, like this another one, gamma ray telescope, Compton Space Gamma Ray Observatory in 1991, and this is Fermi, still in use. So I'm studying data collected by Fermi, and it has actually two types of detectors. I will just explain to you. So when the gamma ray hit this detector, so it's not called a telescope anymore, it's the detector. It hits the inside of, so it goes through the detector, right? But by chance, some gamma ray will be stopped by the atoms of the detector itself. And then when it hit the atoms, the energy is converted into particle, right? Because of E equals mc squared. So the one photon is converted into two elementary particles. One of them is an electron, and one of them is a positron.
正电子，
对，这是
一个伽马光子会变成一个电子，一个正电子反物质。
Yes, this is actually the inverse process of what you heard about of annihilation, right? When matter and antimatter they touch each other, they annihilate and become pure energy. That pure energy is light, and so the inverse process is one particle of light convert back into two particles, and we can detect the motion of the positron and the electron inside the detector, and then we reconstruct the path of the original gamma ray. So this is, so you can imagine it is a very uncertain method, but so we relied on very accurate computer programming, and well, the computer on board of the Fermi has responsibility of telling us that where and how energetic is that one single gamma ray photon. So we are just counting photons. We are not looking at light. We are counting how many particle of light has hit the telescope. and this is the gamma ray burst monitor. This is actually here. So this one is this one, and these guys, these guys. So they serve the same similar detection principles. But these are directional. So these are shields that the shield out the gamma ray photons from the off-axis directions. So we know that if this detector detects a gamma ray photon, it must be somewhere from this angle. So if we put a bunch of these kind of detectors on board, then we know which direction is that gamma ray source. Because if there is one source here, then we expect these face-on detectors to detect more photons than these detectors facing at the other way, at the other direction, right? So, but there are still ways to, if you really want to form an image, then we can still do it. So this is another way to form an image. This is the integral gamma ray space telescope. So on board it is, so here we have detectors. This is just like a CCD in your iPhone. But then we don't know. I just told you, if we just let the gamma ray photon hit the CCD, we don't know which direction it is, right? So we make a shield, a coped mask. So it is a mask, but with some part of it blocked by metals. So the gamma ray cannot pass through the mask, but can pass through the hole between them. So it forms shadow on the CCD. So by computer coding, we can reconstruct the direction of the original gamma ray photon by the shape of the shadow on it. So these are very difficult tasks, but the engineer has access to do it, so we can observe a lot of gamma ray sources in the universe, like some of the AGNs that Serena just talked about. So it consists of central black hole and accretion disk, and then two jets, bipolar jets. And if our line of sight is along the jet, we see it as an AGN, right? And there are other type of jets in the universe, like the black hole binaries. It accretes black holes, like this is like the type 1A supernova, but just replaced has the right job replaced by a black hole. And there is another one. This is actually type 2 supernova, which will form. Theoretically, type 2 supernova is connected to gamma ray bursts, because we observe in the universe so many explosions, but just one-time explosions. It doesn't repeat. So it's like there's one bomb in the universe in this direction. It goes off, and then it's forever. But in some other direction, there's another bomb. So the frequency of the observation is about 1 or 0.07 gamma ray bursts per day we can observe in the universe. So we think that they are formed by type 2 supernovas when a giant star collapses into a black hole, and the matter is ejected so quickly, so that it reaches relativistic speed. And then if you know Doppler effect, right? We just talk about Doppler effect, right? If it's so Doppler shifted, it forms it produces a so-called beaming effect. So everything is beamed in this direction. So it only ejects all the energy into this direction. So the energy the light is so blue shifted. Even if it emits as a visible light or radio wave, it is blue shifted upscattered to X-ray or gamma ray. And then we call them gamma ray bursts. And so this is one of the leading theory, the conventional model of gamma ray bursts: a black hole, a giant star, the center of the giant star collapses into a black hole, and then the jet goes through the surface of the original star, and then in this interaction, so it takes the matter out into this cone, and then because it's so it is not periodic, so it is random. So how the black hole emit material inside the jet is random. So some material will be faster and some will be slower. And if the faster materials catch up the slower one, and so just hit the slower guy, like you're running, but you can only run on one track, and there's one guy ahead of you who is much slower, and you hit him, and then hit him, you create sound, right? But in the space, we create no sound. But so all the energy are converted into light, and this collision is so energetic, so it creates gamma rays, and then we are here, somewhere here, the Earth. So we observe this jet as a gamma ray burst. So so these gamma ray bursts, as I told you, it was discovered by the Vela satellite in 1967, and up to now it's already 50 years, and we still know almost nothing of them. So, and this is why we have to build and refine the gamma ray astrophysics. And I hope you will join this. Some of you will join this this journey of scientific research into high energy astrophysics, because we really know nothing. And what we see is this. So this is the spectrum we see, the blue curve. And so we just guess which process create this blue curve. Was it a Planck? So it's just black body like our sun, but the sun is too narrow. So if you look at the sun, if you plot the spectrum of the sun, it is this red curve you will get. And so you can see it doesn't match, right? But another theory is the electron is, so there are intense magnetic field in the jet. So and there are also electrons, right? There must be electrons in the jet. So there will be magnetic field going crazily here, and there are also there are also electrons in the material going through the magnetic field. So when electrons interact with magnetic field, it emits synchrotron radiation. So you will learn it if you study physics in university, like third year, or I don't know, maybe graduate school, I don't know. But then this is actually one of the simplest explanation, because scientists always sort of seek the simplest explanation. If the simplest case does not apply, then we go to the next step and find a little bit more complicated theory in order to explain the observation. This is science. So this is the simplest electron synchrotron radiation. It doesn't fit either. So one of them is too narrow, and the other one is too broad. So nothing can we we cannot explain the gamma ray burst emissions by these two theories. And up to now, there are so many different theoretical consideration to try to explain the data. Like in this two plot, the data are in these dots and cross are the data points and the uncertainty or the data point. And you see this is pure synchrotron, and this is a synchrotron plus one thermal emission like the sun. And well, in this case, it seems to fit, and in this case, it also seems to fit, but it cannot be two different mechanisms for one observation, right? So there must be something wrong here, and we don't know why. And there are even more trials. I plot this because I was involved in these studies, so just forget it. And come to this final part. I hope this is not too up to this point, it's not too boring. And there are even higher energies that we can observe from the universe, like much more higher than gamma rays, but we just call them very high energy gamma rays because we are running out of names. So, but then but up to this point, we can actually detect them on ground. We don't need to send a space telescope, or yet we just need a very big telescope array on ground. Why? I just told you gamma ray cannot penetrate the atmosphere. But if it is too high energy, it can penetrate some part of the atmosphere, and then the photon hit the atoms in our atmosphere, and then it creates particles, like I just told you, right? It is stopped, and the energy, because light cannot be stopped. If a light is stopped, it must become something else. It cannot be light anymore. So it creates particles. When gamma ray goes through the atmosphere. It hit the at some point hit the atmospheric particles, and it create like protons or some heavier atoms. And then these atoms will hit another atom. Hit another atoms in the atmosphere, and it becomes a cascade. It is like a chain reaction. So if we can detect these cascade particles on the ground, we can reconstruct the original gamma ray. You can see this is so difficult, right? Because the scale here is of kilometers. So we need telescope arrays kilometers wide away from each other. And then this is so complicated. This is just one case, right? This is just one particle, and we detect so many gamma ray particles at the same time, right? We cannot tell this set of objects, hey, just emit, please, just one photon at a time. No, it emits a bunch of gamma rays and hit the atmosphere. It doesn't care. So you imagine that it is a complication. It is a combination of these different scenarios at the same time, and then we have to build, well, clever enough computer program to identify them. So but actually we are not detecting the particle itself, because particle cannot be detected, right? What I just told you is completely wrong. The particle interact again with the detectors and create some other signals that we can detect. One of them is called the Cherenkov radiation. So you ever took a boat, right? And then you can see when you look at the water, you see the wave front going out, right? It is Cherenkov. It is Cherenkov radiation of water. But how can I play the movie?
It was playing.
It was playing.
Yeah.
Did it?
No.
Here? No.
Yeah, it's playing now.
Oh, yes. So you see, imagine this is a boat. This is the wavefront what we see, but actually it is created by circles. All right, this is a shock wave, and when the particle, so when the source of wave is traveling faster than the speed of the wave in that medium, in this case it's the water. When the boat is going faster than the wave speed of water wave, it creates shock wave. So here, back to the astronomy, when the particle cascaded in our atmosphere cascade, when the particle speed is faster than light, it creates a shock wave. The shock wave is called Cherenkov radiation. I hope you have a question, right? I just told you something is going faster than light.
It's not possible.
It is not possible, yes. But why? We observe it.
It's not light.
It is light.
It is.
But it is not free space. It is in our atmosphere. So light is slower in a medium, right? Right. It is like when light is going through your glass. It is slower. It refract, right? Refraction is just another manifestation of the change of the light speed, right? So light in the atmosphere is slower, a little bit slower, and then the particle it creates can sometimes go faster than the speed than light. So it is what created the Cherenkov radiation. So you can only see Cherenkov radiation in medium. You cannot see it in vacuum. So this is why ground-based telescope is useful, because we are covered by atmosphere. Lucky we, right? We have an atmosphere. And so this is one of the examples of the Cherenkov telescope. We detect the light of the Cherenkov radiation, and then we reconstruct the very complicated shape of particle cascade to reconstruct just the one single gamma ray photon from the universe. And this is another one. So it is very high tech. It looks very high tech, right? This is laser, and this laser are used to fix to change each panel of the telescope mirror. So this is not one single dish. It is composed of different parts of reflecting parts, right? Because we have to adapt, because the atmosphere is not static. It has wind, right? That's why stars twinkle when we look at the star, right? Twinkle, twinkle, little star. Because the light is bent, and also the particles will be bent by the movement of the atmosphere. So we have to adapt to that movement. So the telescope is actually moving when it's observing, and we have to use some guide to tell the telescope how to move. So this is the adaptive optics for Cherenkov telescope. And this is yet another very, very large. I think part of it is already in operation, but it is still building. It is still in progress because it consists of hundreds of telescopes. You can't build it at the same time. So it is expanding. It is in Chile, the CTA Cherenkov telescope array. And well, this is how we construct. If we observe in this part of the dish, so it is brighter in this part, but it's dimmer here. So we know, okay, for this dish, we detect the particles are coming from this way, right? Because here it is brighter, right? And then we combine this information from many telescopes, and then we can finally raise the point of incidence of the gamma ray. And then finally, this is already out of electromagnetic astronomy, but this is still considered as high energy astronomy. So I would very briefly talk about it. This is the neutrino astronomy. So we can detect not only photons, now we can detect neutrinos. It is a very light elementary particle, which is, I think this is the lightest particles that human has ever detected. So we are still not confirmed if neutrinos has mass or not. Right, but it is very probable that it has some mass. And we can detect them because in those very violent astronomical phenomena as the gamma ray burst, the black hole, supernova, they all emit neutrino. Actually, the sun is emitting neutrino right now. Every second, billions of neutrinos passing through our body with no feeling at all. Because neutrino is not, it is electromagnetically neutral. So it doesn't feel the EM, electromagnetic force, and it's so light that it doesn't feel gravity at all. So it just passed through the Earth like nothing. But some of them may hit the atoms, and in I don't know how many billions of billions, just one single neutrino will undergo reaction with one atom of the Earth, and then we are trying to detect that one single reaction out of billions of billions neutrinos passing through us. So this is the telescope itself, located down under the ice in the South Pole. So you can see this is the telescope. The telescope is 3,000 meters long. This is down to the sky. But it's very easy to build. So you just melt the ice and then put down the detector into the ice, and then the water freeze again, and you have a free telescope. And then why do we want to do it? Because we want the Earth to block other contaminations, other signals that we don't want, other signals that are not caused by neutrino. We doesn't want it. So we detect the neutrinos. We are detecting neutrinos coming from the North Pole. We are detecting the neutrinos coming from the North Pole and going through the Earth, and then it hits one of the particles inside these long tubes in the South Pole. It is how we do neutrino astrophysics. It's very exciting, and it's very difficult. And if you ever become a neutrino astronomer, you may be able to go to South Pole to do this experiment yourself, and you can do experiment with penguins. So this is one of the detectors that are put into these tubes. So I think there are like how many? So many, 5,000 optical sensors in one tube. So there are tens of thousands, hundreds of thousands of these kind of detectors put under South Pole. And so come to the final part. We want to know the universe, the nature of the universe, and so we observe the universe. This is why scientists are doing their job. So we want to know more, but in the process of knowing more, we often discover that we know so little. So there are a lot of excitations and unexpected observations that we find. So science is a process of trying to refining and tuning our understanding of the universe. For example, this is our galaxy. I just showed you in the first part of the talk, right? Just here. But now recently we find out that our galaxy, our Milky Way, looks like this. In the past, when the detector were not powerful enough, we doesn't see these two loops. It's called the Fermi bubble. It is discovered by the Fermi Space Telescope, and nobody knows why. So I just nobody knows why. How? This is the excitement of science for us, right? Even if it is so close to us, we are just living here or here, right? We find out these unexpected observations just recently. Like I think it's discovered in 2008 or 2009. So yeah, there are so many different processes. As I know that you are students that are interested in science. So I'm trying my best to sell my expertise to you and try to pull you into this this kind of excitement that you will get. Of course, you will also get boring computer programming, and I'm not lying to you, because you have to do your work. But after doing your work, after plotting those graph again, and then doing whatever your boss telling you to do again, and then finally you come with maybe just one very little conclusion. But this is your contribution. So this is the excitement that I feel I want to share with you. So there's so many different things that you can work on. You will never be sort of topics, and but you may be sort of funding and salary. I'm sorry. And also one very final slide I want to show you is the gravitational wave. So another new job opportunity, right? So now we are listening to gravitational waves, not looking, but listening. We're listening to the frequency of gravitational wave passing through the Earth. So there are a lot of new excitement coming in, I hope, recent years, and then it is the right time for you to join. So this is the end of my hopefully not boring talk, and thank you. If you have any questions, just ask.
I just have one comment， 就是，David 等于从这个天体物理或者高能物理的这个天体物理的最开始历史发现，一直推动到了这个现在。实际上发现就是引力波的发现是最近几年的事儿，它等于开创了一个新的天文领域，就专门通过观测引力波来这么一个新的，相当于一个新的门类。以前是不可能有这个门类的，只是停留在理论阶段。所以就是非常，我也是一个天体物理，就是说宇宙学的一个迷吧，就是叫什么，就是一个粉丝。然后听到这些，其实我自己个人很激动。你说同学们实际上是有机会，未来如果你感兴趣的话，像那位女同学，她说她学物理开始觉得特别没有意思、没有用处，但实际上你的最终的贡献可以就把人类的这个整个的所有知道这些东西多出来这么一点点， 就像刚才他就提到的，就是有很多非常未知的东西，就近10年、近20年，不断的发现，所有人都解释不了的一些现象，这都是人类已知的这个界限，所以就等待同学们如果以后也想做科研，就在这些界限上去突破一点，扩充人类的整体的知识。
So yeah, I just have one more thing because I forgot to talk about the polarization of gamma ray bursts. But well, Nima is going to show you now in the lab tour. So how to detect polarization? Just I think in Serena's talks you have talked about polarizations like the tangent. So Nima is going to show you in the lab how we can build instruments to detect polarization. So it's not theory anymore; it's practical. So you can get your hand dirty now. So yeah, any question I ask or
Yes, I noticed that there are 2 types of supernova, but you mentioned the usage of supernova, but I don't know why it can be used to detect the distance of different stars, and I find that these 2 types. I want you to share us more information about this topic.
okay, yeah, sure. So the type 1A supernova is called one of the standard candles in the cosmological ladder. Wow, and as I told you, the right dwarf has a mass limit. It cannot exceed that mass limit. It is actually called the Chandrasekhar limit. It's 1.4 solar masses. If we put more than 1. More, if the right dwarf is heavier than 1.4 solar masses, the electron degenerate pressure cannot sustain its gravity, its self-gravity, and it shrink. So it is always this 1.4, maybe 1.3 something. Well, it depends on how fast it spins, because you know the centrifugal force will counteract gravity a little bit. It helps a little bit, but it's close to that range. So uncertainty very small, and so every right dwarf explodes at more or less the same brightness. It is like you buy a light bulb. The light bulb tells you that how bright is light bulb, and then you observe the same kind of light bulb on a distant mountain, and it's so dim. And then by how much dimmer the light bulb is maybe 100 times dimmer, then you can calculate the distance, right? Because light travel, well, the light emitted by a stellar object, by this kind of stellar object, will be in spherical waves, right? So the decrement of the brightness will obey the inverse square law, right? Or some other law if you find out it is not spherical wave, it is beamed, like in gamma ray bursts, and then you have another formula to calculate. But you have some mathematical knowledge to calculate how much dimmer is it, and you can translate that decrement of brightness into distance. And you ask, oh, so I can calculate how far away is the right dwarf, but how far away is the other star? It is a very good question. So well, if we only find the right dwarf and if we only find the type 1A supernova by itself, we cannot calculate the star around it. But if there is some star around it, is so close that they are mutually gravitationally attracted, so we can treat them as a single entity. It's actually called the star cluster. So more or less, the other star, maybe one star is more or less to the left or to behind the type 1A supernova, maybe 3 light years. But who cares? Because it's so far away, it's like thousands of light years away. For example, if this is 2,000 light years away, and there's one star beneath it, it is like 2 more light years behind it. So it is 2,000, okay, 2,000 plus or minus 2. But it's still very accurate, right? So you're right. So we have to, when we tell you, whenever you heard about some scientific news, most of the time the writer would only tell you how accurate we are. But actually, the most important thing in science is how uncertain we are. because it is the uncertainty that consists of science. If you have 100% certainty, it is not science. It is just a belief, right? I believe something, right? Yeah. Not everything is science. Like I love my family. I believe it because it is just personal opinion. But science is not personal opinion. It doesn't matter who said it, right? It is the data who talks about the truth. So you have to know how uncertain it is. So this is a very good question. So you can actually calculate the distance of the stellar cluster, or even a very far away galaxy. Like the galaxy. One galaxy is like hundreds of thousands of light years across. So if the supernova explode in front of the galaxy, then we may be wrong that the center of the galaxy, of the distance of the center of the galaxy from us, right? Because we will be off by how many 50,000 light years. It is huge in the scale of human, but it is nothing for the universe, like because they are billions of light years away. Just 50,000 more light years. Who cares? Well, but we have to care. It is this uncertainty that we have to care. We are very careful in science. So I hope I answered your question.
Yes, of course. And I have another one. The time the supernova lasting is very short. So why you can detect the position as such a short time? I think it's very
So it's another good question. It's in the earlier time. It is just by incident. So we look at this galaxy, but it just happened at the time of observation. It exploded, and nowadays we have supernova surveys, all sky surveys, by astronomers, by telescopes all around the world. So we can observe some very interesting. Well, we expect the Type 1a supernova to be on the galactic plane. Most of them should be on the galactic plane of galaxies. But I won't go into detail. But then, so we are interested in this region. We expect to see some Type 1a supernovas to go off in some galaxies. So there are galactic surveys that continuously collecting data, and by looking at the data, by digging up the data, it will be your task if you are going to do a grad school student. Be tasked to going through very, very huge pipe of data, and then to just find one supernova, and to just write the one paper that you are required to graduate. But it is science, so that by that way we can collect so many data of supernova. Just to look. You can say it is a waste of time, but we don't just observe. You don't just study the supernova itself, right? If we look at the galaxy for a long time, nothing explode, but we can still look at the galaxy itself because we have observed it so long a time. So we can study the galaxy itself in much detail. So there's no waste actually. Yeah.
I also major in physics, but in China, I know that there are little people study physics. So physics is not very popular. So I want to know that what do you do after you graduate? Yes.
Okay, this is a practical question. I think in China it's already loads of physics graduates more than in Hong Kong. In my class, I have 40 classmates. Only I think that 40 classmates consists of the whole, and then five of us were studying astronomy, and then that is more or less all the students studying astronomy in my year in Hong Kong. So 5 out of 7 million. So this is a problem in general for pure science students. Like nowadays we want, everyone wants to study economy, right? But studying economy doesn't imply that you will be rich, right? Studying about money doesn't imply you will be rich. And for the same reason, studying about physics doesn't imply that you must become a physicist, right? Studying about science doesn't imply that you must do science. But it is not in my opinion, of course. So it's just an opinion. I'm very cautious about giving advice to students, but I always tell them, it is not the knowledge you know which matter. It is the education you receive in the university it matter. It is training as a physics student and makes you think more logical and critical and to evaluate problem independently, right? Doing research teach you do this. You teach yourself, not your boss. Your boss gives you some problem and you teach yourself by solving those problems, right? And then it is this skill you can take it through. I think it is not right. I am not American at all, but it is true that every aspect of the society need logical and critical thinking. So you can just take this skill to whatever you can be a banker, right? Why not? Because we have to analyze data, right, from the stock market of the whole world, right? If you cannot just guess, right? You want to earn money. This is practical, right? I can be wrong about gamma ray bursts, but who cares? If I put my whole all my money into that one stock, and I just guess it will raise, what will happen? 50% of the time you will be bankrupt, right? This is practical. So I hope this advice will be useful for you. But if you think differently, it's okay. It's just a piece of small advice. Yep.
What would happen if
It's okay. It's okay.
what would happen if people fall into the black hole?
You will die.
Just
What else?
where he dropped into the
You will be pulled. You will be like a spaghetti.
Yes.
Yes.
So he will die.
By the tidal force.
Actually, before you can feel it, you're just vanished.
Yes. You will be just
particles and
before you feel feeling anything, you will already be decomposed into elementary particles. So no pain. It's a great.
Will he be possible to have a time travel?
What do you mean? So
If he fall into the black hole, will he?
Nobody knows because this is most. I think I am also interested in these kind of questions, but the problem is, in my opinion, I would have to be very careful because many of my colleagues here are black hole theorists, and they won't be happy if they heard me saying this. I think what happened inside the event horizon of a black hole stay inside the event horizon of a black hole. It is not science, right? You can think about it, but it is mathematics. I am not saying that their work is nothing. Their work is very valuable, right? Maybe in the future we can detect something from the inside of a black hole, then it becomes science, right? But nowadays the generativity tells us that nothing can travel through the event horizon from inside the black hole. So those are mathematics, but they are very highly skilled. So I am not discrediting any black hole theorist, but I think that I cannot answer scientists. I cannot answer anything any question about the inside of a black hole because I don't know. Yeah.
I have some question about the neutrino detector. And I've heard another kind of neutrino detector. There's some kind of big ball on the ground, and there's many sensors.
Yes.
So many sensors around the pool. But as I see from that picture, there's not so much sensors to detect the neutrinos. As far as I know, the neutrino, there's so few neutrinos so that it's very hard to detect just one neutrino and react with the atom. So how could it achieve the goal to capture just a little neutrino in such a low possibility?
Yeah. So I think this can be the last question, right? Because we are running out of time, very behind schedule. But I want to try to answer you so quickly because the well, actually the detector numbers, if your detector is good enough, it doesn't matter how many detectors you have. But actually, I bet what you see is just one small part of the picture of the neutrino detectors. There are actually so many tens of thousands of detectors around the pool. You're talking about the pool, right? So some detectors for example, in Japan they have neutrino detectors, but they don't have ice glazers, right? There are no big ice you can melt, so they have to build. So actually, what particle does the neutrino interact is the ice particles in the South Pole. It hit the ice, it's water molecule, and then it emits the light that the detector can detect. So actually, the detectors are just there to look at. So you imagine yourself in a dark room, and suddenly there is one flash, and you know, okay, there is one neutrino. So if the detector is advanced enough, you can just have one, right? Because if your detector is infinitely powerful, just put one there, and it can see through the whole Earth. But no, so that's why we have to put a lot of detectors, and a lot of detectors also helps to triangulate, right? If you have just one detector, then you know it is of that direction, but you don't know how far is it, right? So you need three, right, to triangulate. And so the big pool you mentioned, they build a very big underground pool and fill it with, I think, water and some mixture of chemicals. I don't know what are they, but then they hope out of the billions of neutrinos passing through the pool, one of them will interact with the water or with the liquid molecules, and then emit light, and then the detectors around the pool, the side of the pool, can detect the light. So it is that difficult. You are right. It is so difficult, but somehow humans achieve it. Yeah. So I think we can go to the lab,
Yes.
show you the polarization.